Let's define what it means for a CTL formula to be equivalent to an LTL formula. This concept is actually very similar to that of equivalence between two CTL formulas. So let phi be a CTL formula and psi be an LTL formula. They are said to be equivalent if they are satisfied by exactly the same LTSs in the same states. Formally, if for any LTS M and state S of it, M in S satisfies phi according to the CTL semantics, if and only if M in S satisfies psi according to the LTL semantics. Now let's prove that two of the formulas we discussed before and claimed to express the same safety property are indeed equivalent. Remember that C1 and C2 are atoms. We want to show that the CTL formula for always not C1 and C2 is equivalent to the LTL formula always not C1 and C2. According to the definition of equivalence, we must consider an arbitrary LTS M and an arbitrary state S0 in it, and show that M in S0 satisfies one if and only if it satisfies the other formula. So let's fix M and S0, and let's see what it means for M in S0 to satisfy our CTL formula for always not C1 and C2. According to the semantics of for all always, it means that for any path pi and any position I on it, M in the ith state Si of that path satisfies not C1 and C2. Which, by the semantics of negation, conjunction, and atoms, means that it is not the case that both C1 and C2 are in the labeling of Si. So far, we applied the CTL semantics of connectives and atoms. Now it's time to make our way towards the LTL property shown in blue, so let's apply some LTL semantics. The fact that not both C1 and C2 are in the labeling of Si can be rephrased as saying that the ith suffix of pi satisfies not C1 and C2. By the way, remember that this is how we write the ith suffix of a path. And furthermore, since this happens for all positions I on the path, what we have here is an LTL always formula. So this is equivalent to the satisfaction of always not C1 and C2. Finally, since our statement is universally quantified over all paths in the LTS that start from S0, this means precisely that our LTL formula holds for our LTS in state S0. So we proved what we wanted by a chain of equivalencies. This time, because it was quite straightforward, we showed the proof as a forward chain of equivalencies, but you can regard the process of proving this as starting from both sides, the brown one from the top and the blue one from the bottom, with expanding the semantics of the temporal connectives in CTL and LTL respectively, and meeting somewhere in the middle. Now let's prove that our formulas for liveness, namely the CTL formula for always, R1 implies there exists eventually C1, and the LTL formula always R1 implies eventually C1, are equivalent, where R1 and C1 are atoms. So again, let M be an LTS and S0 a state in it, and we want to show that M in S0 satisfies one if and only if M in N0 satisfies the other. We start by extending the semantics by expanding the semantics of the CTL connectives in the first formula. M in S0 satisfies it, just in case, according to the semantics of for all always, there exists a path pi such that for all positions I on it, M in its ith state Si satisfies the inner formula R1 implies for all eventually C1. And this just means that if 1 in Si satisfies R1, meaning R1 is in the labeling of Si, then M in Si satisfies the right-hand side of the implication, which is a for all eventually formula. Finally, we apply the semantics of for all eventually to expand that into a statement made for all paths pi prime that starts in Si. Namely, we want that for all states of that path, C1 holds. That is, C1 belongs to their label. And we stop here for now, because we have fully expanded the semantics of the CTL connectives and atoms in this formula. Next, we do the same thing for our LTL formula, shown in blue. M satisfying it in state S0 according to the LTL semantics means that each path pi in M starting in S0 satisfies it, which means by the LTL semantics of always that all suffixes pi I of these paths pi satisfy the inner part of the formula, which is an implication. So applying the semantics of implication, we expand this into an if-then statement where we also applied the LTL atom semantics for R1. And finally, applying the semantics of the LTL eventually connective, we obtain the conditional existence of an index J that points to a state Si plus J further down on the path from Sj, where C1 holds, meaning C1 is in its labeling. In summary, we obtain that satisfaction of the LTL formula is equivalent to the property shown in blue at the bottom. The routine part of the proof is now done, where we simply expanded the semantics of the CTL and LTL connectives, respectively. Now we are left to prove the equivalences of these expanded properties. Property 1 representing the satisfaction of the CTL formula, and property 2, the satisfaction of the LTL formula. So we are left to prove that 1 and 2 are equivalent. That is, each implies the other. Let's start by assuming 1 and proving 2. To prove 2, we let pi be any path in M starting in S0 of the form S0, S1, and so on, and I be any position on this path such that R1 is in the labeling of Si. We must find a J such that C1 is in the labeling of Si plus J. To this end, let's take the path pi prime of the form S0 prime, S1 prime, and so on, to be the ith prefix of pi, denoted pi I. Note that pi prime is therefore a path starting in Si, and the J's state in pi prime, denoted by S prime J, is actually the I plus J's state in pi, denoted as I plus J, for any J. We now apply property 1 to the path pi and the position I to obtain this implication. If R1 is in the labeling of Si, then something holds. And since we know that the left-hand side of this implication holds, namely R1 is indeed in the labeling of Si, this is actually our assumption, We obtain this for all property from the right-hand side of the implication, which we can further instantiate to our path pi prime. In short, we instantiate property 1 to pi, I, and pi prime, thus obtaining that C1 is in the labeling of S prime J. But S prime J is the same as Si plus J, so we proved what we wanted, namely that C1 is in the labeling of Si plus J. Let's visualize the proof that we've just done on a picture of the unwinding tree of an LTS M. We knew property 1 and wanted to show property 2. For this, we considered a path let's say this one, pi, and a position I on it. So let's say here, so let's say we have the state Si here at position I, where R1 holds. So let's say that R1 holds here. And what we wanted was to find a further state on this path where C1 holds. So somewhere further down this path, we wanted that C1 holds somewhere after Si, somewhere on the path pi. Now, we prove this using property 1, which for any path, including our path pi, and for any state on it where R1 holds, including our state Si, it guarantees that on any path starting from there, in particular, including on our continuation on this same path, so including on pi I, the suffix starting from I, there exists such a state where C1 holds. So we are guaranteed that somewhere on this fragment, we have a state where C1 holds, let's say here. So this gave us the state that we wanted, where C1 holds. Now, let's prove the converse, namely, assume 2 and prove 1. To prove 1, let pi be a path starting from S0 and I a position on pi such that R1 holds on its ith state, Si. Moreover, let pi prime of the form S0 prime, S1 prime, and so on, be a path starting from that state Si. So S prime 0, the first state on that path, is the same as Si. Now it's time to apply property 2. We will apply it for a path pi double prime that starts as pi, so it starts with S0 up to I minus 1, starts as pi, and continues from point I, continues as pi prime. This path, pi double prime, also has R1 holding on its ith state. So according to property 2, we can find a later state on pi double prime where C1 holds. Which also gives us a position on the path pi prime where C1 holds, which is what we wanted, and the proof is done. Let's again visualize the proof we just did. To prove 1, we consider the path pi, let's say this one, a state Si on it, let's say this one, on which R1 holds. So let's assume R1 holds here on state Si. And a path pi prime starting from Si, some other path, let's say, so this is the one that is currently shown in brown, is our path pi. And let's say we have another path that starts in Si. Let's say this one. This is going to be the path pi prime. And what we wanted to find was a state on pi prime where C1 holds. So we wanted to show that C1 holds somewhere here on the path pi prime. To achieve this, to prove this, we used property 2. For the path, which we called pi double prime in our proof, that starts as pi and switches direction to become pi prime, rather than continuing as pi from position I. Since R also holds on the I state of path pi double prime, property 2 gives us a later state on pi double prime where C holds. So we have some state somewhere here, let's say here, where C1 holds. Since this occurs in pi double prime after the ith position, this is necessarily a state on pi prime, which is exactly what we are looking for. So property 1 is proved. Okay, this concludes the proof of equivalence between the CTL and LTL properties, both expressing the discussed liveness property.